All right, Titans, welcome back for some more solving systems of equations with quadratics. Calvin is here because he said my jokes aren't very funny, so he wanted to tell one of his jokes.
Why can't basketball players go on vacation?
Why can't basketball players go on vacation? I don't know.
Because in basketball, you're not allowed to travel.
Ah, you're not allowed to travel. Traveling!
Goodbye.
Right, get out of here. Okay, so today we're going to work on systems of equations, and specifically we're going to do it with one linear equation and with one quadratic, which is kind of like the problems we were looking at yesterday on those word problems. To start though, I want to do a warm-up back from IM1 just to kind of refresh you on how we solved systems of equations in IM1. We actually had three ways to solve them. We did elimination, which was when x and y were on the same side of the problem. We solved by graphing, where we graphed the two and we found where they crossed. And then the third method we used, which is what we're primarily going to use in IM2, is substitution. So when I go to solve this, I notice that y equals 2x minus 4. Well, if that's what y is equal to, and this also has y, then we can substitute 2x minus 4 in for this y, because y equals this, so this can replace y. So we can now write it as 2x minus 4, that's our new y value, equals negative x plus 5. And at this point, we just have a multi-step equation. We need to get our x values to the same side. So I can add x to both sides. 3x minus 4 equals 5. Solving for x, add 4 to both sides. 3x equals 9. And then finally, we can divide both sides by 3. And x equals 3. Now what you might remember from IM1 is x equals 3 is not our full solution. When we solve these, we're actually trying to get an ordered pair. So I do know that my x is going to be 3, but how do I now find my y value? Well, since I know x is 3, I can take this value and I can either plug it in right there, because that's what x equals, or I can plug it in right there, because that's what x equals. It does not matter which one you plug it into, you will get the same answer. So I'm going to choose this one. So if I rewrite it, I get y equals 2x minus 4, y equals 2, and then instead of x, I'm going to replace x with 3, minus 4. So 2 times 3 is 6, and 6 minus 4 is 2. So my y value is 2. The solution to this system is the ordered pair 3, 2. Again, if I took 3 and plugged it in here, I would get negative 3 plus 5. And what's negative 3 plus 5? Well, it is 2. So again, doesn't matter which equation we plug it back into, we still get the same answer. Now, if we take that exact same problem and we solve with graphing, let's show what we get. So the first equation, y equals 2x minus 4. Linear equations, hopefully we remember that this number is our y-intercept. So we start at negative 4. The number attached to the x in linear is our slope, or our rise over run, or rate of change. So since it's positive, we're going to go up as we move to the right. And we're going to rise 2, run 1. So rise 2, run 1, put a point. Rise 2, run 1. Same thing, I'm going to do it as many times as I can to fill up the whole graph. And if I connect those dots, that is the graph of y equals 2x minus 4. My second equation, the y-intercept this time is positive 5. My slope is negative 1, which is the same as negative 1 over 1. And since it's negative, we're going to go down as we move to the right. So we're going to go down 1 over 1, down 1 over 1, down 1 over 1, etc. until we get that whole line. And we said our solution is where the two graphs cross. So if I go to where they intersected, right here, That is the ordered pair 3, 2. So if we go back to the warm-up, this was the exact same problem, just not on a graph. But when we solved it and we got the answer was 3, 2. Well, what does 3, 2 have to do with the graphs? Well, 3, 2 is where the two graphs cross. So when we solve a system of equations, it doesn't matter what type of equations they are. When we solve a system of equations, what are we really finding? Well, we're really finding where do the two graphs cross? Where do they intersect? Which point or points do they have in common? All right, so systems of equations, we can use them not just for linear equations, but we can also do them with other types of equations, such as quadratic equations. So in this example, we are given a system of equations. And just to clarify, system of equations means we have more than one equation. In this case, we have 2 equations, and we're trying to find a common solution. Or in terms of a graph, we're trying to find where do these cross. So, if we have this system, we can use substitution, just like we did in IM1 and on the warm-up. So I know that y equals 2x plus 7, and I can plug that in for the y in the other equation, substitution. So I can rewrite this as 2x plus 7 instead of y, right, substitute it in, equals x squared plus 4. Now it says to solve for x. Well, to solve for x is a little bit trickier now because we have x squared, which means we have to solve a quadratic equation. Luckily, you guys have practiced this a lot. You know how to solve by factoring, solve by completing the square, and everyone's favorite, the quadratic formula. So for these examples, I'm going to use the quadratic formula, just to make sure we're getting extra practice with that. First thing with quadratic formula is I need one side to equal 0, right? Standard form. And I also want to keep my x squared positive, so I'm going to leave it here. I'm not going to move it to the other side and make it a negative x squared. I'm going to leave it here. So I'm going to make this side become 0. So I'm going to subtract 2x and subtract 7 so that those go away. But that means I also have to subtract 2x and subtract 7 from the right side. So we end up with the equation 0 equals x squared. Negative 2x doesn't have any like terms, so it's just going to be negative 2x. And then we're going to combine these, 4 minus 7, to get negative 3. And we now have standard form, which we can use the quadratic formula. This one, I believe we could also factor it, and it is set up nicely as well for complete the square, but we're going to use the quadratic formula. A is 1, B is negative 2, C is negative 3. And now we get to plug it in. X equals negative b plus or minus the square root b squared minus 4 times a times c all over 2a. You might hear the echo in the background. That's my son. He knows the formula now. Pretty impressive. All right, so as we go, negative 2 is positive 2. Negative 2 squared is negative times negative, so it's positive 4. And then we have 2 negatives, so this becomes plus 4 times 1 times 3, which is 12, all over 2. Which, when I simplify, gives me 2 plus or minus the square root of 16 over 2. Square root of 16 is a perfect square, so we get 2 plus or minus the square root of 16, which is 4 over 2. And then we can use our Dorito chip, divide each of those by 2, and we get 1 plus or minus 2. And we can do 1 plus 2, which is 3, so x equals 3. But we can also do 1 minus 2, which will give us x equals negative 1. Now, hopefully from the warm-up, you remember that once we found our x coordinates, we weren't done. We need to find the ordered pairs. And in this case, since we found two different x values, that means we're going to have two separate solutions, two different ordered pairs. I know that for the first one, my x value is 3, and for the second one, my x value is -1. So how do we now go back and find the y coordinates? Well, we have x, so we're going to take x and plug it back into the original equations. And if I go back to my equations, they're right here. And does it matter which equation we plug it into? No, you get the same answer either way. So I can either plug it into this bottom one, which has the squared in it, or I can plug it into this top one, which is just a linear equation. This one either way is pretty much the same difficulty, but I'm going to go ahead and plug it into this one. So if my x is 3, I'm going to plug it in right here, and I get y equals 2 times 3 plus 7. 2 times 3 is 6, and 6 plus 7 is 13. So I know that when my x value is 3, my y value is 13. That is one of our solutions. For the second one, I'm going to take -1, and I'm going to plug it in. And I can plug it into the same equation again. Y equals 2 times x, which is -1, plus 7. 2 times -1 is -2. And -2 plus 7 is 5. So we end up with the ordered pairs 3, 13, and -1, 5. Two different solutions. If we take that exact problem and we graph it, how do we find the solutions? Well, I went ahead and did that. I graphed those exact same equations, and I found that the points of intersection were -1, 5 and 3, 13. Do those points look familiar? -1, 5, 3, 13. So again, just as a reminder or to hammer home the key point, when we're solving a system of equations, we're figuring out where do those two graphs cross, or what ordered pairs do they have in common. So for that particular problem, the 2 points they have in common are -1, 5 and 3, 13. Yes, graphing is much easier, especially with Desmos, but we do want you to learn how to do it by hand, which is a lot of fun and good practice of the quadratic formula. All right, before we solve a couple more, just want to go over this page, which is thinking about the different ways or how many possible solutions we can get when we have one linear equation and one quadratic. So again, as a reminder, if we have a linear equation, it's going to be a line. And if we have a quadratic equation, it's going to be a U. So one option, we'll be right back.
You have a gate key or no?
Yes.
Okay,
Good. Thank you. Can't believe it, they're trying to kick me out of here. I'm here all night. That's right, Umesh is the man. Okay, so if we think about a quadratic and a linear, how many different ways can they intersect? So if we have a parabola, one possibility, like our example we just did, is that they will cross in two different places. So if they cross in two places, you get two solutions. Is it possible for them to only cross one time? Well, yeah. And again, there's multiple ways we could do this, but one example would be something like this. It only touched right there. Or you could have something like this as well. Okay, but usually it's going to be like this one. So we can get two solutions, or in this case, since they only touched once, we can get one solution. What's our last possibility? Well, with quadratics, we can get two solutions, one solution, or it's possible to get no solutions. So how would I get no solutions? Well, if solutions are where they intersect, we just have to make sure that the other graph never touches, right? Where do these two graphs cross? Nowhere. They don't. So this would be an example of no solutions. So as we solve systems of equations with one linear and one quadratic, it's possible for us to get two solutions, one solution, or no solutions. All right, let's solve some. This first one, we've got the linear equation here, we've got the quadratic equation there, and we know we can substitute. So I'm going to substitute one equation into the other. You could also substitute this whole thing into that y. It's the same thing. But if I do it this way, I get negative 2x plus 4 equals 4x squared plus 2x plus 5. And now we need to solve for x. Well, to solve for x, we need to put it in standard form. My x squared is positive, so I'm going to leave it here. To move the negative 2x, I'm going to add 2x to both sides. To move the positive 4, I'm going to subtract 4 from both sides. And that gives us 0 equals 4x squared plus 4x plus 1. And now we're going to solve the quadratic equation. We can use, again, factoring. Complete the square wouldn't be a good option because our a value is not 1. But we can always use the quadratic formula. So a value is 4, b is 4, c is 1. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. And then we simplify. X equals negative 4 plus or minus the square root of 4 squared, which is 16, minus 4 times 4 times 1. Hey, that's also 16 over 8. Now, for the sake of space, I'm going to simplify it right here. 16 minus 16 is 0. And then I'm going to simplify again. What's the square root of 0? Well, the square root of 0 is 0. So I'm left with negative 4 plus or minus 0. Well, if we add or subtract 0, nothing's going to happen, so I don't even need that part. So I'm left with x equals negative 4 over 8. What does negative 4 over 8 actually equal? Negative 1/2. So this was one of those kind of unique ones where we actually only got one solution, right? There was only one x value, and it was because our square root was 0, right? Our discriminant was 0, so we only get one solution. And we know that our x value is negative 1/2. But we also know that we need to find the ordered pair where these two graphs will cross. So I still need to find the y coordinate. Well, if this is x, right? X is negative 1/2. How do we get y? Well, we're going to take our x, which was negative 1/2, and we're going to plug it in to either equation. I'm going to choose the linear one. It's going to be easier. And so now I can do y equals negative 2 times x. Well, my x is negative 1/2 plus 4. Negative times negative is positive. If you have 2 halves, you have a whole. So this is positive 1 plus 4. So y equals 1 plus 4, which means y equals 5. So my solution to the system is negative 1/2, comma 5. That is where the two graphs will cross. If you don't believe me, let me show you a graph. And right here, we've got our linear, we've got our quadratic. They cross right there, which is the point negative 1/2, comma 5. Negative 1/2, comma 5. Math. All right, let's try another example. Like I said, we could plug this in for this y, or we could take this and plug it in for that y. Doesn't matter. If I do it that way, I get 3x squared plus x minus 3 equals negative 4x minus 7. We're going to solve it by setting it equal to 0, put it in standard form so that we can use the quadratic formula. So add 4x to both sides. 7 to both sides. And by doing that, this side of my equation is now 0, which is essential for standard form. And then if I combine like terms, I have 3x squared plus 5x plus 4 equals 0. We're going to use our quadratic formula. A equals 3, B equals 5, C equals 4. And we're going to plug it in. Bless you, Calvin. X equals negative B plus or minus the square root B squared minus 4AC all over 2A. Whew, this is some good math. I'm getting tired. All right, X equals negative 5 plus or minus the square root of 25 minus 4 times 3 times 4, let's see, 12 times 4, 48, all over 2 times 3. Now something jumped out at me. It may have jumped out at you too. 25 minus 48. What type of number is that going to be? Well, 25 minus 48 is a negative 23. What happens if we get a negative in our square root? Well, we get no real solution. So, can I solve this? No. There are no real solutions. Okay, so let's think about this for a minute. Our solutions to a system are where the two graphs cross. So if I solve it and I get no real solutions, where do the two graphs cross? They don't. Very good. And to prove it, if I take a look at that pair of equations, we've got the quadratic right here. And then we have the linear equation right here. And as you can see, those two graphs never touch. So there would be no solutions. So again, no real solutions is a possibility. It just means that they don't have any common solutions. They never cross. All right, one more example for today. This is a little bit bigger here. So last example of quadratic and linear. Again, we can take this and we can substitute it in for y. X squared minus 4x plus 5 equals x plus 1. To solve this quadratic, what do I want one side to equal? I want it to equal 0. So I'm going to subtract x and subtract 1. Subtract x, subtract 1, which gives me x squared minus 5x plus 4 equals 0. It's now in standard form and it's set up perfectly for my quadratic formula. A is 1, B is negative 5, C is positive 4. Plug it in. Isn't it sad when I don't sing the song? Gosh. All over 2A. All right, so we get negative 5, which is positive 5, plus or minus the square root of 25 minus 16. Let's go ahead and simplify this right here. 25 minus 16 is 9. And what's the square root of 9? Well, the square root of 9 is 3. All over 2. Since we don't have any square roots, we can simplify this to get our two different x values. We can do 5 plus 3 is 8, and then divide by 2. 8 divided by 2 is 4. We can also do 5 minus 3, which is 2, divide by 2, which is 1. So we know that our two x values are going to be positive 4 and positive 1. Now, that's good, but we're not done. because all we found were the x's, our x's, and we need to find the ordered pair where they cross, so we still need to find our y values. So again, to find the y values, we just take x and we plug it in. You could plug it in up here, it's going to be more work. Plugging it into this one is easier because all I have to do is 4 plus 1, and 4 plus 1 is 5. And then same thing here, I have an x value of 1. 1 plus 1 is 2. And so our solutions to this system of equations are 4, 5, and 1, 2. What do these solutions represent? Well, it represents where the two graphs would cross on the coordinate plane. Represents two different options where if I was to plug in 4, 5 for both of them, it would work for both. And that's it for today. So solving systems of equations, we're going to use substitution and make sure that when you solve it, you always go until you get the full ordered pairs, which you could have 2 ordered pairs, you could have 1 ordered pair, or it's possible to get no solution. But make sure you don't stop at just finding the x's, right? Finding the x's was good, but we also need to find the y value. Have a great day, Titans.
Bye.